Let's look at the formal definition of linear combination. If v1, v2 up to vk are a set of vectors from Rn, and c1 up to ck are scalars, then this right here is a linear combination of v1 up to vk. So I don't have any examples written here, but I'm going to make a couple up. Let's look at this. I guess I'll call this example, no, I'm not going to number it, is 3, 9 a linear combination of 3, 0, and 4, negative 2. Now I want to answer this question, and also I want to say, if so, find the coefficients. Coefficients being the c's that go with them. So we'd set this up as the equation c times 3, 0 plus c2 times 4, negative 2 equals 3, 9. And so this would be the system 3, 0, or the augmented matrix 3, 0, 4, negative 2, 3, 9. And of course, this is my C1 column, my C2 column. Now, before we solve this, let's use some geometric intuition to figure out if this is going to be a linear combination or not. So we're looking at the xy plane, and the two vectors we're looking at are 3, 0 and 4, negative 2. So I'm going to draw those in purple, and I'm going to make them sort of big so we can see them. So 3, 0 is going to be over here, 3, 0. And 4, negative 2 is going to be further over and then down. So 4, negative 2 is going to be here. And we're asking, can you get 3, 9 out of these guys? Well, 3, 9, let's see, that's going to be here and then way up here. So is there any way to add multiples of these guys together and get that? And it might not be obvious, but the answer is going to be yes. The idea here is, think about this. If you take this vector here, just using copies of that, you can get anywhere along the x-axis. So the idea is we want to take this and stretch it over far enough that we could then take this one and add a negative multiple onto it and back up to it. So what we should be able to do is go way over and then back up until we get to this up here. So the answer is going to be yes. Let's work it out now. We've got to solve that system. That's an easy system to solve, but I'm still just going to use octave for it. Let's see, my matrix here, m equals 3, 4, 3, and then 0, negative 2, 9. And it gives me this. Well, it gives me that because I typed it in. If I take its reduced row echelon form, it gives me that. So this reduces to 1, 0, 7, then 0, 1, negative 4.5. So the answer here is yes. Is it a linear combination? Yes. Find the coefficients. All right, let's see. This top line here says that C1 is 7, and the bottom line says C2 is negative 4.5. So we could write 7 times 3, 0 minus 4.5 times, what was the other one? 4, negative 2. That's going to give you 3, 9. All right, let's do another one. I'm going to do this one in, I'll do this one in three-dimensional space. Is 317 a linear combination of I'm going to pick these deliberately. 2, 0, 0, 0, 5, 0, and I'm going to put 2 more on here. Three, 3, 3, and then 6, negative 1, 2. All right. So to just answer this question straight up, we can just write it as a system. We'll do C1. I'm actually going to be a little bit lazy. Do C1 times this, C2 times that, C3, C4. Being a little bit lazy meaning I'm just going to jump straight to writing my matrix. So the matrix we have here is going to be 2, 0, 0, 0, 5, 0, 3, 3, 3, 6, negative 1, 2, 3, 1, 7. So this system will tell us whether or not that can be written as a linear combination. So let's type this into Octave and row reduce it. All right, so my matrix is 20363, 0, 5, 3, minus 1, 1, and 0, 0, 3, 2, 7. So let's see, 2, 0, 0, 0, 5, 0, 3, 3, 3, 6, negative 1, 2, 3, 1, 7. So yeah, that's the correct matrix. Now let's row reduce it and see what we get. Okay, that looks it's not too bad, but let's change that to fractions. All right, it's doing this. I don't like it when it starts splitting it up into columns like that, so I'm going to make this bigger. I actually have to do 2 things to make that happen. I have to slide this over and then actually make it bigger. And it's not going to automatically update. I'm going to have to make it print it again. All right, I'm going to copy that below here. So it gives us 1, 0, 0, then 2, negative 2, 0, 1, 0, negative 3/5, negative 6/5, then 0, 0, 1, 2/3, 7/3. All right, so what does this mean? Well, we get a solution, so the answer is yes. Let's write that out. We get solutions. So yes, it is a linear combination of that set of 4 vectors. Now let's think about this for a minute. Let's write it out. This is C1, C2, C3, and C4. We're going to get a general solution out of this. C1 is going to be negative 2 minus 2C4. C2 is negative 4/5 plus 3/5 C4. C3 is 7/3 minus 2/3 of C4. And C4 is a free variable, so it's just C4. So you get infinitely many ways to do this. All right, so you can pick any value you want for C4. If somebody said, give me a particular solution to this, you just pick a value. 0 would be the easiest one, and plug it in for C4, and that would give you a set of coefficients that get you that would get you 317 as a linear combination of these guys. Now, I want to think about this geometrically for a minute. I want to draw these 4 vectors in here. So let's see, x, y, and z. And I'm gonna copy this and bring it down so I can. I want to draw these in. So these are x, y, and z in that order. All right, if you look at these things, this first vector is 2, 0, 0. So if we were to draw that in, it's going to have an x value of 2. So it's going to go along this line. 0, 5, 0, that's going to look like this. So let's think about this for a second. If you only took linear combinations of these 2 vectors, you could use those and get anything that lies in the xy plane. So these next 2, once you've got this third vector in here, I'm going to do it in purple, 3, 3, 3. So that's going to come out 3 units, then 3 units parallel to y, then 3 units parallel to z. So it's going to end somewhere up here. Actually, I'm going to draw that in there. So we get this vector here. Now this vector goes out of the xy plane, and so when we've got that, that's enough to get any point we want. So if we just have those first 3, that's enough to get any point that lies in R3, and so that's enough to get 3, 1, 7. So that last vector is really redundant in some sense. 6, negative 1, 2, what would that even look like? 6, so we go down here 6 units, negative 2 units parallel to the y-axis, and then 2 up here. So it would look something kind of like that. So anyway, we only need 3 of these to get it. And the fact that we have an extra one over here just means there's more than one way to get to it. So that's why we wind up having infinitely many solutions. Let's see. I think we'll stop here.